Hi, in this session we'll start the third module, which is multiple integrals. Okay, so multiple integrals basically the extension of the familial integrals which you have studied in our lower classes. Okay, so in that cases it was like integral had to integrate to be f dx. So there was one variable which was integrated over an interval here. But in the multiple integrals you will have more than one independent variable. Okay, that's the difference. Okay, you will have there can be dx dy will be there, or there can be dx dy dz will be there. So this is basically the extension of the single variable integrals which we have studied in our lower classes. Okay, if there are two variables in our integral, we will call the integral as double integrals. Okay, so we will be focusing on double integrals in the first few sessions. Okay, if there are three variables, it will be triple integrals. Okay, so all the theory is remarkably very similar. So if you know double integrals, you can very well learn triple integrals because it's just an extension only. Okay, so there is nothing new to learn from here. Only you need to know the basics of integration. Okay, if it's a double integral, that is suppose it has two variables, you will denote the integral by this symbol. Okay, that means there are two integrals here. Okay, so here there can be some function of f of xy. I don't know what it is. It will be some function like that. Okay, and there can be some variations of x here. Okay, so this is the notation for that. If there is three integrals, you will have three variables. Your integration will be like this. It will be called triple integrals. Okay, so just like our single integrals, we can say a double integral is also like this. It will be some f of xy dx dy will be like this, or it can also be written as f of xy dy dx. Okay, and similarly there are triple integrals also which you can carry over. Okay, so here one thing, very important thing you have to know here is that the order of this integration is very important. If you change the order, possibilities are there that your answer can be different. So order of integration is actually very important. Okay, so if you are writing dx dy, you should try to integrate in that order itself. Okay, now how to perform the integration? Okay, that is actually very simple. You will be performing the integration from inside to outside. Okay, that means first of all you have dx here, so first you will have to integrate this with respect to x. Okay, just like our partial derivatives, when you had dou f by dou x, what you do, you will take f, suppose f is a function of x comma y. Well, how will you find dou f by dou x? You will be integrating this f, you will be differentiating this f with respect to x, keeping y constant. So similar concept here. So when I ask you to integrate fxy with respect to dx, it means you will have to keep y constant and just integrate the function with respect to x. For example, suppose you need to integrate xy dx dy. Okay, so you can see that dx is lying inside, so first you will be doing the integration with respect to x here. So it will be the outer integral, we will not do it first, we will only do the inner integral first, then we will come to the outer integral. So what is the integral of this xy with respect to x? The integral of xy with respect to x is, integral of x is actually x square by 2, and y is a constant with respect to this integration because we are integrating this with respect to x only. Okay, so I hope it is clear how to write this x square by 2 y. Okay, don't apply the parts rule here because here y is to be treated as a constant. Okay, and now once you have done that, okay, now once you have done that, now you can integrate this with respect to it. Sometimes there will be some limits here, sometimes there will be limits like that, there will be 0 1 1 2, so in some cases there won't be there, but usually in our sessions, in our module, we will always be evaluating only definite integrals. Okay, so there will always be limits here, so it is not necessary. Sometimes there cannot be, there are integrals in which there are not limits also. Okay, so suppose you have done this integration, now you can do the next integration. Okay, now you have to integrate this function with respect to this y. So what will you do? Here x is to be treated as a constant, so when you integrate this with respect to y, you will get this as x square by 2 y square by 2. Okay, see, so there is nothing new, only the familiar integration rules are to be applied, nothing new is there. You are just extending the integration to one more step, that is what is called double integrals. Okay, so that is the basic idea here. So I hope it is clear. And similarly, if it is written as dx by dy, first you should integrate with respect to x, then you should integrate with respect to y. If it is written as dy dx, first you should integrate with respect to y, and then you have to integrate with respect to the order is very important because for some functions it may be the values will differ depending upon the order. Okay, these are very good functions, it has some property, we will discuss it later. That is why even if you integrate this with respect to x or y also, you will be getting the same answer. Okay, that's enough. Okay, so I hope this is clear. What do we mean by double integrals? So I hope the integration technique, evaluation techniques is clear to you. So we will do some examples also, but generally this is the method. So once you have understood double integral, it is easier to understand triple integrals also, because in the case of triple integrals there will be one more variable coming. That's it. Okay, so first you will integrate with respect to x, then you will integrate with respect to y, and then you will integrate with respect to z. Okay, so that is the only thing, you are taking one more step ahead. Okay, that's it. Okay, so that is what is meant by double integrals. Okay, so as I told you, just as when you are integrating over a single variable, for example, if you are integrating over f dx, you know that actually here we are integrating over an interval. Okay, and f may be a function which will be defined over this interval. So basically this will give the area under that curve. So many geometrical interpretations we can make of this integral. Okay, so similarly, when you are actually integrating along some, maybe suppose it is some a, b, c, d, okay, some f dx dy, actually what is happening is that you are actually integrating this along some so basically if you look at this one, you can see that x is varying from a to b. Okay, x is varying from a to b, so you can see that the variation of x is from a to b, just like the variation in x here was from a to b, here the variation of x is from a to b, and the variation of y is from c to d. Okay, so variation of y is from c to d. Okay, so you can see that this will actually define a region in the xy plane. Okay, so where there is a variation of x coming, there is a variation of y coming, so basically this will define a region R in the xy plane, where basically there is some variation of x, some variation of y here. So in the case of definite integral of one variable, you had an interval here. In the case of this double integrals, you will have a region in the xy plane. Okay, so that's the essential difference. Okay, when you have a triple integral, you will be having a region in the space. Okay, because there will be one more coordinate coming, which is z. Okay, so the dimensions will be increasing. Okay, that is the basic idea. Okay, rest everything is just the same. You just evaluate, you substitute, and you can do the questions. Okay, so I hope it is clear. There is no new concept coming here, only the same old integration itself. The only difference is you will be having more variables here. Okay, so this is so now we'll be focusing on double integration, and double integrals, I told you, it is actually defined over a region in the plane. Okay, because you are getting a variation of x and also a variation of y. Okay, and also we will discuss some important applications of double integrals, especially to calculate areas and volumes. Just like we used definite integrals to calculate area, double integrals could also be used to calculate areas and volumes. We will be discussing those formulas later in this session. Okay, so now let us go to some problems here. So this is a notation for double integral. Okay, so as I told you, usually double integral, it will be, you will have some limits, or simply they will tell you that you will have to take dx dy over the region R. The region will be given to you. That means suppose the limits of the region would be given to you, or it will not be given to you depending on the problem. So if you know the limits, you can just apply the limits here. It will be 0 to 1 or 1 to 2, whatever may be, or you can simply write R. So this notation means you are actually integrating this f of xy with respect to x and y over this region R. That is the meaning of this notation. So we'll write this as simply integral over R f of xy dx dy. Okay, or in other words, there are some other notations also. We can also take dx dy for short as dA. dA means actually area, so it can actually be dx dy or dy dx also. It depends on the context there. So dA basically means it is actually dx dy or dy dx. Okay, so instead of writing dx dy, you can write in shorthand form like this. Okay, similarly, when you have some volume there, it will be like integral over v. Okay, if you have a triple integral, we will write it as triple integral over some volume v, where you are going to integrate the function of f of x y z over dx dy dz or dz dy dx, or depending upon the order. But once you have written the integral, your order is very important. Okay, you have to evaluate only according to that order. Okay, in some textbooks they also write this as dv. Okay, so dv essentially means either dx dy dz, dy dx dz, or whatever may be. So that is the meaning of this dv. Okay, so I hope the notation is clear. Now let us try to do some simple problems. So how will you do the problem? First look at the limits there. In the first set of problems, the limits will be given to you. There is nothing to do nothing extra to do. They will give you the limits there. You will have to directly evaluate. Okay. In the second set of problems, we won't give you the limits. We will just tell you that I am taking this region in the xy plane. From there, you have to write down the limits by yourself. Okay. The region will be given to you. From there, you have to identify the limits and then you have to calculate. Okay, and the third set of problems, we will have some applications related to this volume and area. Okay, so these are the three set of problems which will be coming in double integrals as well as triple integrals also. Okay, so let us try to do some problems here. Okay, as I told you, the integration is to be performed from inside out. Okay, perform from inside out. So we'll start with the inner integral, evaluate them, keeping the other variable constant, proceed to go to the next integral in order and so on. So okay, so as I told you, the order is always very important. And remember one thing, always in all the problems will be given a definite integral only. Okay, so the final value in a definite integral will always be a constant. So keep that in mind, because if you know that, if whatever maybe suppose it is integral 0 to 1 x square e raised to x dx, even if you evaluate this, the final answer will always be a constant, because you will be substituting these values there. So final answer should be a constant, unless it is an indefinite integral. The final answer will always be a constant. Okay, so why I am telling you is that some people will do the integration and they will get the answer as a function itself, so that will be wrong. Okay, if it is a definite integral, the final output should always be a constant. Okay, now let us do one problem here. So first we will be finding double integrals over rectangular regions. Okay, what do you mean by rectangular regions? I'll tell you now. Suppose we have to evaluate this integral. Okay, just have to evaluate this integral. Now observe this. Before evaluating this, look what is the variation of y. Y is varying from 2 to 4. Okay, so y is varying from 2 to 4. Suppose this is 2, this is 4. Y is varying from 2 to 4, and x is varying from 1 to 3. How can I know that? I will just look at the limits here. Y is varying from 2 to 4, x is varying from 1 to 3. So when you plot that region, what will you get? You will be actually, your variation of x and y is forming a rectangle like this. Okay, so that is why this region is said to be a rectangular region. Okay, so what is a rectangular region? Rectangular region is when both the limits of x, y are constants, you will always be getting a rectangular region. Okay, so you will ask me what is non-rectangular. We will discuss about non-rectangular regions in the next session. So basic idea of rectangular regions is both the constants of limits of integrations will be constant. So if it is happening, constants are coming as limits of integration, always your region would be rectangular. Okay, just keep this in mind. It's not required for examination, but this idea is very simple. Okay, so now we are going to deal with rectangular regions in this session. Okay, in the first set of problems, I will give you the limits here. In the second set of problems, I will actually give you the rectangle in the xy plane, and looking at the rectangle, you have to identify the limit of the x and y also. Okay, so it is very easy to identify. X will be varying from this point to this point, and y will be varying from this point to this point. So it is very easy to identify also. Okay, so in the first set, we will give you the limits. In the second set, only the region will be given to you. Looking at the region, you will have to identify the limits. Okay, in the next session we will have non-rectangular regions also. So you will be given a non-rectangular region, then you will have to find the limits. So in that case, the constants of the limits of integration won't be constants. There can be functions. We will come to that in the next session. Okay, now we will try to evaluate this. How will you evaluate this one? Okay, so as I told you, first evaluate the inner integral. So we keep the outside one there itself. So second one, we'll evaluate this one with respect to y here, because y is given. So when you integrate this with respect to y, what will you get? You will be getting this as 40y, because I am integrating with respect to y, minus 2x into y square by 2. Why is it coming so? Because your x is a constant, only y is a variable here, so it will be y square by 2 in the limits dy. Okay, so when I substitute the values of this y, I will be getting it as integral 1 to 3. What is the answer here? So please correct it. So what is it? It is 160 minus x into 16, okay, minus 80 plus x into 4. Okay, x into 4 dx. Okay, so please correct me if I am wrong. But this is the basic idea. So it will be integral 1 to 3 80 minus what is it? 12x. Okay, dx. Now it's a single variable integral. You can easily evaluate it. That's nothing but 80x minus 12x square by 2 in the limits 1 to 3. Okay, so you know that the final output is always a, what is happening? Final output when you substitute this 1 and 3 will always be a constant. Okay, so that doesn't mean that the inner integral will be a constant, because you can see that inner integral here was not a constant because x, the factor of x is still lying there. But once you have done the x integration also, the final output will anyway be constant. Okay, the inner integral will not be constant because there can be factors of x and y coming there also. Okay, but the final output should always be a constant. So if you are getting the final answer as some 12x square, remember your answer would be wrong, because always you should get the final answer as a constant only. Okay, so let us try to do some of the problems also. Now this is a question which has been asked in K2 also, so let us try to do this one. How will you do this one? It's a very simple thing. So if you look at this integration, the first integral is with respect to dx, so first you will integrate this with respect to x, keeping y constant. So it is actually integral 0 to 1. So y is a constant, and what is the integral of 1 by root 1 minus 1 x square dx? It is sine inverse x by a. Okay, so if you don't remember, it is basically here it is sine inverse x. Okay, so please go back to your integration formulas, try to learn every formulas. We will be using them extensively, so just recall all those formulas and the methods also. So we will be using extensively those methods in this session. Okay, so you will have to recapitulate all the previous formulas, okay, which you have studied in your lower classes. Okay, so when I first integrate with respect to this x, my y is a constant, that's why I can keep it aside. So it will be integral 1 by root of 1 minus 1 y square into integral of this one, which is nothing but sine inverse x in the limits 0 to 1 dy. Okay, so what is it? Actually, it will be actually integral 0 to 1 by root of 1 minus y square into sine inverse 1. So what is sine inverse 1? Sine inverse 1 is actually pi by 2 minus sine inverse 0 is actually 0. So we will be getting this one. Okay, so dy. Okay, similarly, when your pi by 2 is a constant, so I can take it outside, it will be simply integral 0 to 1 by root of 1 minus y square, that is also pi by 2 into sine inverse y in the limit 0 to 1. So we will be getting this as again pi square by 4. Okay, so even in the first step itself, you can take this one root of 1 by root of 1 minus y square to the outside of the integral. So that you also can do. For example, it will be like this: integral 0 to 1 by root of 1 minus y square into integral 0 to 1 by root of 1 minus x square into dx dy. Okay, this is just to basically simplify the steps only. It is not required. If it is comfortable for you, you can do that. Okay, so you can straight away write here it as pi by 2 into 1 by root of 1 minus y square, and you can take the pi by 2 outside. Okay, just as I have done here also. So in some textbooks, they also have used this approach. Okay, so no, everything is just the same, but I hope the idea of calculating the integral is easy to you. Okay, there is nothing, no concept coming here, only the old methods of integrations are being asked. Now the one thing to bear in mind is that first you will be evaluating the inner integral first, then we will be coming over to the outer integral. That's the only idea which you have to remember. Okay, so moving forward, this is the value, we have got the value here. Okay, now let us do this question also. Please try to do this question with me also. Okay, so how will you do it? So it is actually integral 1 to b, first it is dx, so I will integrate with respect to x first. So what is it? So y is a constant here, so what is integral of 1 by x? Integral of 1 by x is actually log x in the limit 1 to a. So what will you get? Integral 1 to b, so dy is lying there, 1 by y, so it is actually log a minus log 1. Okay, dy, what is log 1? Log 1 is 0, so it is actually integral 1 to b 1 by y log a dy. Log a is a constant, you can take it outside, and when you integrate this 1 by y, what will you get? You will get it as log a into log y in the limits 1 to b, that is actually log a log b minus log a log 1. Log 1 is 0, so this will be your answer. Okay, very straightforward calculation. Okay, that is, you are only doing the same integration problem 2 times. So in the triple integrals, you will be doing this 3 times. That's it. So there is no new concept coming. Only thing is that you are just repeating the integral process. That's it. There is nothing new here. Okay, and I hope it is clear. Okay, now we will compute the integrals and region is given to you. Okay, so that is also very simple. Okay, so these are some questions for you. So here they have just mentioned it as RDA. Okay, so I can write this as in 2 ways. I can write this as 6xy square dx dy, or I can write this as 6xy square dy dx also, because basically area is length into breadth, so it is basically dx dy or dy dx also. You can write in any order, but when you write the order, always remember, if you are writing x first, supply the limits of x here. Okay, and then you supply the limits of y there. That's how you have to supply the limits. Okay, here in this case, you have to supply the limits of y here first, then you have to give the limits of x here. Just like this, order should be kept in the evaluation as well as writing of the limits also. Okay, now let us write the limits. Now what is the variation of x here? Okay, this is actually of the form a cross b, where x is basically you will be getting it as, what is a cross b? A cross b is order interval a b, where a is coming from a and b is coming from b. So this region is actually of the form xy, okay, where x is coming from this one and y is coming from this region. So your x variation is from 2 to 4 and y's variation is from 1 to 2. Okay, I hope it is clear. Why is it so? Because this is of the, what is your region actually? Your region consists of coordinates like this, right? Okay, your region consists of coordinates like this, x comma y. And where is this coming from? This is coming from the cross product of two sets. We have studied set theory in your lower classes, so a cross b. Okay, so your points will be coming like this only, a comma b, where a is coming from the first set and b is coming from the second set. So your x is coming from 2, 4 and y is coming from set 1, 2. Okay, so your region is actually like this, where x is varying from 2 to 4 and y is varying from 1 to 2. Okay, so that's the region here. So can you tell me the variation of x here? So x is varying from 2 to 4. So if I write dx here, you will have to write 2 to 4 in the inner integral and y should be written as 1 to 2. Okay, very simple thing. Similarly, if you are writing this way, first you have to supply the y limits, which is 1 to 2. Then you have to supply the x limits, which is nothing but 2 to 4. Okay, now you can do the integration, which is straightforward way. Nothing is there. How will you integrate it? Suppose I am evaluating this. So what is it? Actually, it will become integral 2 to 4. First I am going to integrate with respect to y, which is 6x y cube by 3 in the limits 1 to 2 dx. You can substitute. So then once you substitute, then you will get a new quantity and you substitute, then you again integrate with respect to x. So straightforward calculation. So in this problems also you can check it out. X is varying from -5 to 4, y is varying from 0 to 3 here. This di you can either write it as dx dy or dy dx. Write any one form and try to evaluate. Okay, so try to write in different ways in the first few forms. So it can be 2x minus 4y cube. First if I am writing dx first, so it will be -5 to 4, then 0 to 3. Simple problem, just try to integrate and then find the answer. Okay, so like that you can do all these problems. Nothing new concept is there. Only thing is that you are just using the familiar integration methods. Okay, so if you want, you can do this one also. Okay, this one also, how will you do it? Okay, so if you are writing it as x e raised to xy, then you will have suppose this is dy dx. Okay, what is the variation of y here? Y is varying from 0 to 1, x is varying from -1 to 2. Okay, so first you have to integrate with respect to y, keeping x constant. So it is actually -1 to 2 x e raised to xy. What is integral of that? E raised to mx is e raised to mx by m. So it will be simply e raised to xy by x dx in the limits 0 to 1. Okay, so your x will get cancelled out. So it is actually integral -1 to 2 e raised to xy in the limits 0 to 1. So we will be getting this integral -1 to 2 e raised to x minus 1 dx. Now you can easily integrate. Okay, so don't apply integration by parts here, because it's a very simple function. Okay, you have to integrate with respect to y only. Okay, so what will happen? You will be getting this as a constant there. So this is actually of the form mx. So when you integrate, you should get e raised to mx by m, but your variable is actually y. That is why I wrote it as e raised to xy by x. Okay, but in in the same problem, if I had took the variable of integration as, suppose it is x e raised to xy, suppose I had written it like this, dx dy. So where x varies from -1 to 2 and y varies from 0 to 1, the integration would be a slightly lengthy one, but it's not difficult. It's a slightly lengthy one, because when first you have to integrate with respect to x, now it is written as a product of two functions here. So we'll have to apply integration by parts here. Okay, like what is first function into integral of second function minus second function integral of. So you will have to apply integration of parts, then substitute, then integrate the resultant value with respect to y. So it's a bit lengthy. Okay, so now we can understand that in some cases dy dx would be easier to evaluate. In some other cases dx dy would be easier to evaluate, and identification of this will come by practice. Okay, so you have to do some problems and practice. Try to do all these problems and try to practice them, so that you will know which to do, which variable to take first to integrate. Okay, and whichever variable you take first, always remember, write the limits of integration corresponding to that variable only there. Okay, if you change the order, your answer would be wrong. Okay, and also remember, the order of integration is very important. Okay, so I hope it is clear. Now let us discuss on the application of this in the double integrals. before I come to one is called volume. So before I come to volume, one simple application is integral over r dx dy will be actually area of the region. Okay, it's nothing to discuss here. It's very simple, straightforward application here. Okay, for example, suppose you have a region like this here. Okay, suppose it is x. I'm just giving an example. Okay, suppose your x is varying from 1 to 2 to 4, and y is varying from 1 to maybe 4. Okay, so x is varying from 1 to 4. So this is your rectangular region. You know the area. What's the area of this region? Actually, it will actually, this length is 2, your breadth is 3, so area would be 2 into 3, which is 6. Okay, it is L into B. Now let us apply double integration. What will you have when you have suppose you are evaluating dx dy, or for that matter you can also evaluate dy dx. Suppose you are just evaluating this. So what will you get? So the variation of x is from 2 to 4, variation of y is from 1 to 4. So when you integrate, what will you get? You will get this as integral 1 to 4. Integral of dx is actually just x. So you will be getting x in the limits 2 to 4 dy. So that is, you will be getting 1 to 4 into 2 dy. Again, when you integrate, you will get this as 2y in the limits 1 to 4. So that is 2 into integral y from 1 to 4, which is 2 into 3, which is again 6. So remember, this dx dy will always give you area. So you can write this as a result now. It will be more useful in non-rectangular regions. There I will introduce this formula also, but it is obvious from here itself. Area is, so in the one variable case, area was given by integral a to b f dx, where f is the value of y. Okay, in the two variable case, straight away you can write it is simply dx dy only, nothing, no function is coming here, just dx dy over that region. Okay, that's the area. Okay, now we will discuss the volume. Now volume is actually analogous to the area formula of one variable calculus. So it is nothing but, suppose your function suppose there is a surface z is equal to f of xy. Now you know that z is equal to f of xy is a surface from second module partial differentiation, because you know that if z is equal, here z is equal to x square plus y square, you will be getting a paraboloidal surface there. Okay, or z square x square plus y square plus z square is equal to 1. We will have a sphere. So you can write the value of z from that itself. So basically z is equal to f of xy is actually a surface. Okay, suppose some surface is lying over a region R in the xy plane. Okay, suppose this surface is lying over a region. I'll show the diagram now, but just try to remember. Suppose a region z is lying, f of xy is lying over a region in the xy plane. Okay, so then the volume of the, just like your one variable calculus, the area under this curve was given by integral a to b f dx. Just like that, the volume of the surface under the volume of the solid under the surface will be given by simply double integral over r is f. Okay, f dA. Okay, so this is the volume formula. So volume of the solid under the surface f would be given by just double integral over r f dA, just like your area formula in one variable calculus. So I hope you can relate them. Okay, in the area there it was integral f dx, here it is nothing but integral f dA. Only thing is you are taking the double integral. Okay, so this is the illustration. So you had a surface z is equal to f of xy here. Okay, and this is surface that this plane sheet is the surface there, and this is the region. So this circular region is given here. So if you are looking the volume of, if you are looking at the solid under this surface above this region, you will be getting a what is a cylindrical type surface like this. Not cylindrical, but it is like a cylindrical type of surface coming here. Okay, so how to calculate the volume of that surface? It is nothing but integral f of xy dA. Okay, so it can be f of xy dx dy or f of xy dy dx also. Okay, it's simply that. Okay, and this is the idea of that proof of that. This is the proof of that concept, but it's not required for you. So basically what we are doing is that I am going to fill this volume by so many rectangular cuboidal shapes here. Okay, so just like calculating the area in the one variable case, I am going to fill up this volume by so many rectangular pieces like this. Okay, so that's the idea there. It's not required for you, just you need to just know the formula, substitute and find the answers. Okay, so that is the volume formula. Okay, so in this section they can also ask you the volume formula. We will do one problem like that here. Suppose you have to find the volume of the region bounded above by the elliptical paraboloid. Don't be afraid of these names and all. Just look at the definition of the function. So here your f is given to be 10 plus x square plus 3y square. So your S is actually f of xy, which is this function, and the region is given to you. Okay, notice the formula. The formula is nothing but volume is actually nothing but r f dA. Okay, so you can either evaluate as simply r f dx dy, or also you can evaluate as simply r into f dy dx also. Okay, so only thing is that you will have to supply the limits accordingly. Okay, so what are, if you are applying this one, what is the value of x, what is the variation of x here? X is varying from 0 to 1, the variation of y is from 0 to 2. Okay, if you are using this one, the variation of y is 0 to 2 and variation of x is from 0. So don't forget to write the limits accordingly as the derivative there. Okay, so differential is there. Okay, so you can, what will you get here? So it will be simply be, please try to do any of them. So if I am using this one, it will simply be in double integral 10 plus x square plus 3y square dx dy, where x varies from 0 to 1 and y varies from 0 to 2. Now it is straightforward integration, you can easily do. So integrate this with respect to x. So what will you get? It will be simply integral 0 to 2 10x plus x cube by 3 plus 3y square x in the limits 0 to 1. Just apply it. What will you get? You will be getting it as integral 0 to 2. So it is 10 plus 1 by 3 plus 3y square dy. Now integrate, so you can simplify this also. So it will be integral 0 to 2 31 by 3 plus 3y square dy. Now you integrate with respect to y. So it is actually integral 0 to 2 30, it is actually 31 by 3y plus 3y cube by 3. So in the limits 0 to 2. So no new concepts are there, only the familiar integration concepts are there. Only thing is that you are extending the integration to one more step, that's it. Okay, we are not studying any new concepts, you are just generalizing the familiar one variable calculus. So if you have understood this thing, there is no need to teach you triple integrals also, because triple integrals is just one more extension of this double integrals. So that's it. Okay, so you can so this is the evaluation here. If you want, you can look at these steps also. So that's it. So these are some other questions also. You will have to find the volume. The value of z is given to you. Just apply the formula v is equal to integral over r f dA or z dA, where your z is actually f of xy. Just substitute and give the limits. Okay, so that is double integrals. In the next session, we will be talking of non-rectangular regions. Okay, that's all. Okay, thank you.